Hello, let me welcome you to the presentation of the advanced simulation tool for gas and/or steered bioreactors. My name is Witz. I'm from the spin-off company SimVantage, and we make reactor simulations accurate, fast and easy. So what is the challenge? The challenge, of course, is that the design and the control of reactors is still based on empirical knowledge. There's a lack of deeper process understanding in these bioreactors. And this now then leads to rudimentary scale-up procedures like constant P/V, constant tip speed, constant KLA, geometrical similarity. It doesn't really give a picture about the complex processes which are happening inside the bioreactor. And therefore we have another approach. We use the approach that we ask ourselves, what does the cell or the microorganism feel when they float through the reactor? And this is called the Lifeline approach. And for the Lifeline approach, we need to simulate all the physical parameters within the bioreactor, and then we know what the cells or microorganisms feel in terms of dissolved oxygen, for example, or in terms of shear stress, in terms of nutrient concentration, and so on. And now, how do we get from our physical first principle based reactor scale up and using those cell lifelines with what we have, the geometry and the operating conditions? The basis for all the simulations, all the further simulations, is the fluid and bubble simulation. Building up on the fluid and bubble simulation with the simulation of substrate, where we know, for example, the nutrient concentration, or the dispersed phase simulation, where we can simulate oil droplets which are dispersed in the reactor, but this can also be used for reaction starters, for example. And we can also add a model to simulate the temperature. The shear rate directly comes out of the fluid simulation and can be directly used for the lifelines. And the results of all the other modules also flow into our lifeline concept. But let's start with the fluid and bubble simulation. For the fluid simulation, we use the Lattice-Boltzmann method. What is the Lattice-Boltzmann method? Basis of every fluid movement are the Navier-Stokes equations. And what has been done up to now is that we use the finite volume method, finite element method, or the finite differencing scheme to approximate these Navier-Stokes equations. And these methods are perfectly suited for the CPU, so your main processing unit in your computer. But the new generation of algorithm converts the Navier-Stokes equation into the Boltzmann equation. The Boltzmann equation is an equation of statistical mechanics, and then approximates this Boltzmann equation with the Lattice-Boltzmann method. And this Lattice-Boltzmann method is ideally suited for GPUs, for graphic cards. And as the graphic cards, because of Bitcoin and gamers, because of the graphic cards getting faster and faster every year, we're getting a faster and faster Lattice-Boltzmann simulation every year. And the reason for why this is so fast is because it's highly parallelized, and it's about 10 times faster than the classic methods. And what is important inside the reactor, because we deal with very small cells or microorganisms, is that we model the turbulence correctly, because on the cell level, on the microorganism level, we have very fine turbulent eddies, and these are simulated in the Lattice-Boltzmann directly with the large eddy simulation, and all these turbulent eddies which are smaller than the cell size are modeled with the so-called Smagorinsky subgrid model. And with that, we already can produce very fancy pictures of the flow field within the reactor. But the question always is with simulation results, is that correct? And for that to compare, it's best to take a line throughout the reactor at a certain distance to the steer axis, for example, and then compare physical experimental PIV measurements. It's particle image velocimetry, where you add some particles and then you take two pictures in an extremely short time, and then you see how far they move, and then you know with the time and the distance of the movement, you know the velocity, and then you can bring this velocity into a diagram and compare it to our simulation. Our simulation are the green dots in this diagram, and you see that you get a very good agreement. And with that, you can do your first use case. These are two Intermig steerers with the same turning direction, but different steerer angles. And what is shown is a cross-section through the reactor. The darker the color, the faster the velocity, and the arrows give an indication where the fluid is flowing. And if you now have the task to bring solids from the bottom into suspension inside the reactor, you immediately see that you would choose the configuration on the right, because the fluid field is much more pronounced here on the bottom. With that, we can come to the bubble simulation. And for the bubble simulation, we use a two-way coupled Lagrangian model. What does that mean? Lagrangian means that we follow each of these bubbles directly, and two-way coupled means that not only pushes the fluid, the bubble around, but also the bubble can push the fluid around. This means if you don't have a steerer in your reactor, if you have a bubble column, then you can simulate these fluid vortices which are forming because the bubbles take the fluid with them to the top, and the fluid has to come down at the walls of the reactor. And for the movement of the bubble, that you know where they are going, we solve the Newton's equations of motion. This is simply all the forces which act on such a bubble are summed up. And with the resulting force, we know the acceleration and the velocity and the position at the end of each time step. And because in a production scale reactor, the number of bubbles is so high, we group some of the bubbles together, which have similar properties. And this is called the parcel approach. What the bubbles can do if they move around is that they collide with each other. If they now collide with each other, two things can happen. And to choose what of the two things is happening, we use the Coalescence model of Sommerfeld. Either the two bubbles collide and separate again, just exchanging momentum, or this little tiny film between those bubbles, when they touch, ruptures and a big bubble is formed, and then a coalescence event is taking place. And to decide if either they exchange momentum and separate again, or if a big bubble is formed, you can use the Coalescence model of Sommerfeld, where you can compare the contact time of these two bubbles with the film drainage time, how long this film takes to rupture. And if the film drainage time is longer, then the bubbles just separate again. And if the film rupture time is shorter, and the contact time is longer, then a big bubble is formed. But the bubbles do not only get larger, they also get smaller. And this is called a breakup event, when the bubble breaks apart. And this is mainly caused by turbulent eddies, which are in the size range of these bubbles. Because larger eddies just transport the bubbles around, and the smaller eddies do not have enough energy to tear the bubble apart. And with, for example, the model of Lue and Swenson, you directly get the daughter bubble size distribution. And this means that you can directly calculate if equally sized bubbles are formed, or if a larger and a smaller bubble is formed after the breakup event. And together with the breakup frequency, so how often such a breakup event occurs, with the double bubble size distribution and the breakup frequency, you can model the whole breakup within your reactor. And with this, you can already do first test cases we have a 150-liter plexiglass reactor in our lab, where we test the distribution of the bubbles and the size of the bubbles with conductivity probes. This reactor has 3 Russian turbines, and we tested 5 different flow regimes, some without recirculations, some with recirculation, and different recirculation flow regimes, which are then differentiated by the gassing rate. And this is also experimental validation, which is shown in our paper from Chemical Engineering Science, where you can read that we have a good agreement between the experimental values and the simulated ones. Often, especially in industrial size reactors, it is important to know the power number. So how much power do you have to use to turn the stirrer? And this power number simulation can be done in 2 ways. Either you sum up all the forces which act on the stirrer and multiply these forces on each different parts of the stirrer with the distance to the stirrer axis, then you have the torque. Then you can up all the torques which act on the stirrer and get a resulting torque. And with this way you can calculate the power number. Or you say that all the energy which is brought into the liquid is caused by the stirrer. And therefore, in the simulation, you can sum up all the energy dissipation, all the energy which is present in the liquid, and can then calculate back how much power has the stirrer transmitted to the liquid. And those 2 methods, either with the torque in blue or with the energy dissipation, gives you, as you can see here, the same result. And it gives you the correct result because we did that with a Russian turbine, and the Russian turbine has a power number of 5. And this also agrees overall the flow regime, so coming from turbulent to transitional to laminar, we get all the correct results, comparing with the experiments from Slokanic, for example. And this power number often has a dependency on how fine the grid is, because if you go for a finer grid, you have finer forces on the stirrer, for example, where you can calculate the energy dissipation in a better way. But in our case, you see that you have a very, very low grid dependency. So you can go very low with very big cell sizes and already get a correct power number. And this can also be done for the gassed case and the ungassed case. And it's even more difficult because you have to get the gassed power number correct and the ungassed power number correct. And then, for example, you can compare it with experimental values of Nino and see that you have a very good agreement from the simulation with the experimental values. What is a bit difficult but very interesting is that we can also detect flooding in our simulation. So flooding is when the stirrer cannot distribute the bubbles radially, if it's a radial stirrer, radially anymore. If you think about a Russian turbine, if it's flooded, the bubbles just flow around the stirrer and flow to the next stirrer. And the Russian turbine cannot distribute the bubbles anymore radially because either it's turning too slow or the gas flow rate is too high. And in the simulation, you can see it very easily, but in, for example, stainless steel reactors, often it's the bottom stirrer which is flooded. In a stainless steel reactor, you cannot see this and you lose a lot of efficiency in your reactor if the stirrer is flooded. So what we do to detect the flooding is that we place a virtual cylinder around the stirrer. And now, if the stirrer functions correctly, the flow is from the inside to the outside of this virtual cylinder because the stirrer pushes the fluid outwards. Now, if the stirrer is flooded, like in this picture, then the bubbles go to the top and we have this circulation. And now the fluid and the liquid flows from the side towards the stirrer, and the flow rate of this virtual cylinder changes the sign. And this is what we see here. Here the stirrer is not flooded in the higher RPM range on the right of this diagram. And if you go lower with the rotational rate, then you see that at some transition point, which you can then detect, the sign switches of this flow rate, and then you are flooded in this regime, which is shown on the bottom side of this diagram. And this transitional point you can now compare with experiments like from Wammerskerken, and you see that the experimental value and the simulated values are in good agreement, and therefore we can use this simulation to detect flooding inside a reactor. So we also want to be able to simulate very large bubbles, because especially in non-Newtonian reactors, large bubbles can be present, which accumulate in zones where there is a low shear rate, and the bubbles get stuck, accumulate together, and then break free if they have a certain size. And then you have very large bubbles. And this is still work in progress. And the good thing is that you would be able to simulate coalescence and breakup of these bubbles. If you simulate the whole surface of the bubble, you can simulate coalescence and breakup directly. But what we can do with this free surface model is to model the free surface of the reactor. And if you have a reactor without any baffles, then this vortex is formed. And with the free surface model, we can simulate the vortex. And this is especially important because when this vortex touches the stirrer, then it often comes to foaming. And of course, you have to validate this. And the validation cases were done by Prakash, where you can either compare a picture with the simulated one here on the left. You see a very good agreement. Or for the 500 RPM case, he has given a literature value of the lowest point of this vortex, and you see that this agrees as well. And what you can then do is that sometimes these vortices are used to get more oxygen into the reactor, and this is called surface gassing. And for this we included the possibility to simulate the mass transfer through the surface into the reactor, and then you can simulate how efficient you are aerating your reactor without getting any foaming problems. So now we've mastered the fluid and bubble simulation, we can come to the substrate simulation. And for the substrate simulation we need a passive scalar transport algorithm. We do it with the method of Osmanlich, where we just are able to decide how much which part of the mass which is present in one cell is transported to the next cell by comparing the density distribution vectors which we get out of the fluid simulation. And with this algorithm, which is not very complicated, we can already do simulations like that. This is a reactor without any stirrer, just a bubble column. The bubbles are not shown here for visibility. But what we see here is already the dissolved oxygen in this bubble column. So the oxygen is transferred from the bubbles to the liquid, and within the liquid we use our mass transfer algorithm to transport this dissolved oxygen around. And for the mass transfer from the bubble to the liquid, we use the Eddy-Cell model, because this has been shown that this Eddy-Cell model gives the best results for a normal operation of the bioreactors. And of course we have to validate this as well. We use here the measurements of C, and here's shown a mixing time, that when you add, like for example a salt, how long does it take that you reach the 95% mixing time, so that all 95% of the reactor is within this certain homogeneous concentration, or there are not more deviations than 5% from the average concentration. And this point can be measured experimentally and also with the simulation. And you see here that ideally all points would be on the 45-degree line, but you see that they're in very good agreement and are pretty close to this ideally 45-degree line. But you can do the same for the KLA, so how much oxygen is transferred from the bubbles to the liquid. And you see that here the experimental values and the simulated values have a slightly larger deviation, but this is still a very good result if you think about how hard it is to measure the KLA experimentally correct. So the deviation in the experiments by itself is oftentimes higher than the deviation to our simulated values, so this is a good agreement. So the next thing we are looking at is introducing a disperse phase into the reactor, like for example oil droplets. And these droplets are used for nutrition of cells or microorganisms, and these droplets ranging from 10 to 1000 micrometers, and it would be too costly to simulate each or follow each oil droplet individually, and therefore we use the population balance equation. And this population balance equation just defines certain size classes for the oil droplets. For the explanation, I use here 3 size classes, in green a larger one, in blue the one we are looking at, and in yellow a smaller one. And now if you have a control volume like this box, you know how much convection you have into this control volume of these particles of your size class, how much convection goes out of your control volume. And within the control volume, the particles can coalesce to enter the larger size class, and these particles of the larger size class can break up to enter our size class. And the same can be achieved for breakup to the smaller size class and the coalescence of the smaller particles to our size class. If you now sum up all these processes, you know the rate of change of your particle concentration for your size class I, for example. And if you do that for all the size classes, you know the size distribution of these oil droplets within your reactor. And again, you can do a validation here with the data of Rusadi. The open symbols are the experimental values, the colored lines are our simulations, and you see a very good agreement between experimental and simulated values. And for another oil, for a Conroe oil, you see a slightly larger deviation in the smaller droplet size, but we get a perfect agreement in the average diameter of the droplets. But more interesting than this graphs is the size distribution within the reactor. And here you see this rather large control volumes. Normally you use smaller control volumes, but just to explain the principle. Here in the area around the stirrer, as you would expect, you have a smaller average diameter, and below the gas parcher there's not a lot of shear or turbulence happening. You have larger oil droplets. And then you can do very nice simulations where you start with a high volume fraction of dispersed oil in the top and a low volume fraction of dispersed oil on the bottom. And in the bottom part, of course, you have a lower viscosity, and you immediately see that if you look at the velocities, that these velocities are much more pronounced in the lower half because the viscosity is lower. Now, if the concentration of the oil is because the stirrer is turning and mixing everything together, you can see that slowly we're getting also a turbulent flow field in on the top. And if now all this oil is homogeneously distributed within the reactor, you can see also that the the flow field in the top and the bottom of the reactor is now equal. And the last one of our modules which I want to present today is the temperature. And for the temperature, as you would expect, you can define a heating jacket, for example, and then see how the temperature field evolves over time. Interestingly, we're using the same algorithm as for the mass transport, but now the quantity which is transported is thermal energy. And we can do the same also for submerged tube bundle heat exchangers. And these submerged tube bundle heat exchangers are, for example, used in large-scale fermentation reactor. We can simulate up to 250 cubic meters. That simulations we have already done. And these tube bundle heat exchangers can also be simulated if they cool down or heat up the reactor. But the main source of heat in a bioreactor normally are the cells or microorganisms, and therefore we can introduce massless tracer particles. Massless because the cells or microorganisms are so small that they do not influence the flow field, but they are just transported around by the flow field. And then we can switch up, we can assign every one of these tracer particles a certain quantity of heating or a certain heating power, and then we can see how the reactor heats up because of the heating power of the cells or microorganisms. If you have a biological model, you can also directly calculate the heat generated by that biological process, and this would lead to an even more refined simulation than in this case where every cell has the same heating capacity. And the last source of heating or cooling is in this example is that the bubbles or the compressed air which is pressed into the gas poucher can have a different temperature than the surrounding liquid, and therefore we can also simulate the temperature of the bubbles. And we had one case where there was an unexplained cooling in the reactor, and we could explain that with the cold air which was pressed into the reactor. And of course the cold air heats up if the bubbles rise in the reactor, but the liquid cools down and then gives a heat or a temperature gradient which was previously unexplained but could be explained by a simulation. And with that we come to our cell lifelines finally. And with the cell lifelines we use again dispersed cells which we already have seen. They are massless tracer particles, and we use a representative number of cells because the real number of cells in a bioreactor is just too high for every computer that is available today. But with a representative number of these dispersed cells, we can record these lifelines. We use these massless tracer particles. And an example of this lifeline for the shear can be shown here over time. It's a diagram over time, and if you look at these spikes in the shear rate, you see that this are the points in time where the cells are close to the stirrer in a high shear zone. You can also then define thresholds above which the cell is marked as dead, for example. And you can do the same diagrams for oxygen, dissolved CO2, substrate concentration, or the rate of product conversion if you have a biological model. But even more interesting than this time series of one cell is that we are looking at all the cells. We're asking all the cells to give us their current, for example, shear rate for specific times. And this now leads to these histograms where we have a shear rate on the x-axis. This is a very low shear rate here and a very high shear rate here. And we are asking every one of these cells to give us their shear rate. And if one cell tells us a specific shear rate, the shear rate gets increased by one bin count. And now it's not that interesting to do this for the same reactor for different times, but it's very interesting to do that, for example, for different reactors of different sizes, or if we have a process transfer, to do it for the base reactor and the target reactor, because then we can compare the shear rates of two reactors on the basis of what microorganisms or cell feel when they float through the reactor. And this gives us a quantitative comparison where we then can do scale up with that, because we can compare the shear rate, the dissolved oxygen at specific times, for example, in the fermentation phase. And then we can also generate, for example, scale down models where we look at these histograms at the large scale and then create models of reactors which give us the same histogram in the smaller scale. So to sum up, I've presented the simulation technologies for all bioreactors. It gives unique insights into reactors. We use validated algorithms based on first physical principles, and you can design, optimize, or troubleshoot your reactor in silico. If you're interested, leave me a message at christian.witz@theograz.it or christian.witz@simvantage.com, and I would be happy to get in touch with you to discuss your scale-up, scale-down, process transfer, troubleshooting challenge, and how to convert that in a simulation challenge. Thank you.